Good evening, everybody. It's Friday night, and we're going to talk about improper integrals at section 8.9, several things. So we're going to talk about how to apply a limit definition to improper integrals in two cases. One, when the interval we're integrating over is infinite or unbound, and then two, when the function itself is infinite or unbounded. We're going to use language about convergent, divergent, whether or not a improper integral converges or diverges, and then specifically tie this into integrals or the behavior of x to the negative p. That's going to be an integral from, say, 1 to infinity of x to the negative p, or 1 over x to the p dx. We're going to specifically focus on that for p values in these two intervals. Okay, so types of improper integrals, there are two of them. There's the unbounded interval type, unbounded integrand type. On Monday, we'll deal with unbounded integrand. This video only talks about the unbounded or infinite interval type. And by interval, we mean something like 1 to infinity, where this is we're used to fixed bounds, say 1 to 2 or 1 to 3 or -3 to 10. This is 1 to infinity. That's an infinite interval. And as such, the fundamental theorem of calculus does not apply here. So this is why we're dealing with improper integrals. So we'll look at those integrals, p integrals, use language about converge or diverge. Namely, we're going to define an improper integral with a limit. And then if that limit exists, then that integral will be said to converge. We'll say that integral converges. Otherwise, the integral will diverge when the limit does not exist. And limit notation is going to be a thing. So let's look at improper integrals with an unbounded interval. So say 1 to infinity of 1 over root x dx. Here, that's the same as 1 to infinity, 1 over x to the half. This is a p integral with p being 1/2. And we're going to be in the habit of comparing that to 1. It's less than or equal to 1. So to set up a limit that handles these definite integrals, we're going to say limit as n goes to infinity, and then 1 to n. And so we are replacing infinity in the bound with the letter n and letting n go to infinity. Then we have x to the -1/2 dx. Then once we've set this up, nothing really changes. We still anti-differentiate like normal. Our bounds are 1 to n. We're going to keep those bounds. We'll evaluate from 1 to n, and then once we've done that, then we'll take the limit. So for limit notation, limit as n goes to infinity sticks with us throughout the process. We'd use the power rule, x to the -1/2 plus 1 divided by this new exponent evaluated from 1 to n. Then we'd have limit into infinity. This is going to be 2 root x from 1 to n. We still keep writing the limit notation. We have not applied the limit yet. We'd have 2 root n minus 2 root 1, which is going to be 2. Now take the limit. This first term goes to infinity. The second term goes to -2. So we're looking at infinity minus 2. This is an infinite limit. This limit is infinite. The limit does not exist. This limit in peak represents the area under this curve from 1 to infinity. So I have an arrow here indicating that the pink region would just continue to the right. The curve itself, this curve, 1 over root x, is infinite. That curve is just going to go on forever to the right. It has a horizontal asymptote at the x-axis. So that curve continues on forever to the right. It continues like this. The pink region also just keeps getting bigger. It goes to infinity. So we say the limit is infinite. The pink area is infinite, and the limit does not exist. And since the limit doesn't exist, we say the integral diverges. The integral diverges. And that's the language we'll use when the integral, the limit does not exist. Okay, so just to clarify again, 1 to infinity, the integral, improper integral from 1 to infinity, 1 over x to the half. It's a p integral, p equals a half, less than or equal to 1. What if p were 1? So for a p integral then, and let's look at, how about this time we look at 3 to infinity rather than 1 to infinity. In this case, it really won't matter. Our p integral would be 1 over x to the 1, or just 1 over x dx, and our antiderivative. Let's set up a limit first. We'd have limit into infinity of the integral from 3 to n of 1 over x dx. That's our limit as n gets big, goes to infinity. Antiderivative is natural log absolute value x evaluated from 3 to n. We would have natural log absolute value n minus natural log absolute value 3. This first term goes to infinity. So again, we have infinity minus natural log absolute value 3. That's infinite. And again, the integral diverges. The area under the curve of 1 over x from 3 to infinity just keeps getting bigger. And this is why 3 doesn't matter. It could have been 1. If we'd had 1, we'd have natural log 3. We could have had 50, and it would have been infinity minus natural log 50. We could have had a billion, and it would be infinity minus natural log of a billion. That lower limit doesn't matter because this is a p integral. P was less than or equal to 1, and as such, this integral is diverging regardless of that lower limit. Let's consider another p integral here. P is equal to 2. So here p is equal to 2, which is bigger than 1, not less than or equal to. If we set up our limit n gets big, 1 to n, 1 over x squared dx. With the power rule, we will have the limit going to infinity, negative 1 over x from 1 to n. Before we evaluate the limit, evaluate at the bounds. So negative 1 over n plus 1 over 1. Now, this denominator gets big, which means the whole fraction goes to 0 because it's a fixed number over something getting big. So now our limit is 0 plus 1, and it actually equals something. The limit exists. So similar to the last one with 1 over x to the half and 1 over x. And now with 1 over x squared, we have an infinite curve. This curve just continues forever to the right. We have a horizontal asymptote at x equals, y equals 0, the x-axis. But this question of the integral from 1 to infinity 1 over x squared, it's asking you, what's the area in blue from 1 to infinity under the curve? And this limit is telling us that the area is 1. It's a fixed area, even though that curve is infinite. So here the limit is 1. The area is finite, it's 1, and the limit does exist. So since the limit exists, we say the integral converges. That area is converging. It's converging to 1, while the other areas up here, these areas aren't converging. They just keep getting bigger. They go to infinity. So if we summarize that idea of p integrals are integrals of the form 1 to infinity, 1 over x to the p, or x to the negative p rather. And you have two options. These integrals will either converge or they will diverge. It's one or the other, and an integral can't do both. It can't converge and diverge. It's either converge or diverge. The integral will converge when that p-value is bigger than 1. It'll diverge when the p-value is 1 or less. Okay, let's keep moving on let's look at that same integral from 1 to infinity, but let's change the lower limit. So instead of 1 to infinity, let's use, say, 5 to infinity. So if we look at the integral from 5 to infinity of 1 over x squared dx, this is a p integral, and the p is 2, and that's bigger than 1. This integral will converge. Integral will converge. We know if we set up a limit, the limit will exist, but we just don't know yet what the limit will be until we evaluate the limit. So limit 5 to n, 1 over x squared dx, that antiderivative is going to be the same as before. It was what, -1 over x. -1 over x from 5 to n. And now let's plug in n, plug in 5. So -1 over n plus a fifth. And this first term goes to 0. It's a fixed number over something getting big. And so we get a fifth for our area. Area under 1 over x squared on 5 to infinity is a fifth, not a half, a fifth. And that integral, which represents the area under the curve, converges. It converges to a fifth. This is the language we're using. I bet if we looked at the integral from 2 to infinity of 1 over x squared, it would be a half, is my guess. Okay, what about the integral from 75 to infinity, x to the -3/2? This will converge because p is 3/2. It's bigger than 1. I don't know what it will converge to. We'd have to set up a limit or ask Wolfram. Here I'm asking it to plot this integral, plot the curve from 0 to 500, x to the -3/2, and we're looking from 75 to infinity. So here's 75. The gray area is what we're looking for. It's represented by this integral here. We know it will converge. What does it converge to? I didn't set up a limit, but I asked Wolfram, and here's the code for that, and apparently it converges to 2 over 5 root 3. All right, 2 more to look at as they get more tricky. These are not p integrals, so moving on from p integrals. Let's take the integral from 1 to infinity, natural log x over x squared dx. The area that this integral represents is here shaded below. It's an infinite curve. Question is, does that integral converge or diverge? Does the area underneath converge or diverge? We'd set up our limit like we have here. This antiderivative is going to be handled with integration by parts. I have that substitution over here. I picked u to be ln x and dv to be 1 over x squared. So if we kept going, let's see, this would be from 1 to n also. So limit into infinity, we have negative natural log x over x, and then minus 1 over x. Same antiderivative as before from 1 to n, and we're going to plug it in, and we're going to plug in a 1. So limit into infinity, negative natural log of n, divide by n, minus 1 over n. Subtract the evaluation at 1. So when we do these signs, we'll switch. It'll be negative, so plus natural log 1 over 1 plus 1 over 1. Now, if we evaluate our limit, this goes to 0 because natural log 1 is 0. Term on the n is 1. This term's going to 0. This one, the first term, we have a numerator, we have a denominator. Both are going to an infinite limit. This top negative natural log n, the top numerator, is going to negative infinity. Then n itself in the denominator is going to negative infinity. That's infinite over infinite, and for that we need L'Hopital's rule just on the first term. If we take our derivatives of the first term with respect to n, this is 1, then negative natural log of n is negative 1 over n. And let's see, these next two terms were already 0. We still have 1 on the end. This numerator now goes to 0. We get 0 plus 1. Area under the curve is 1. The integral not diverges, it converges. So this area is 1, which should be strange to you a little bit, or it's finite. It's a finite area. Finite area under a curve that goes on forever. The last one, okay, so I mentioned there the curve is infinite while the area is finite. This improper integral doesn't have 1 to infinity, but both bounds are infinite bounds. And the area that this curve represents, or this integral represents, is here in yellow and blue. That's the curve that we're talking about, and the area we're talking about. I just made one yellow and one blue to differentiate between the two. But to handle this integral, we need to split it up. And I'm going to choose to split the integral into 2, and to split the integral at the value 0. 0 to infinity, negative infinity to 0 of the integral, then 0 to infinity of the same integral. So we're splitting here at 0 at the origin. We could have easily split, at like a half and done negative infinity to a half to infinity, evaluate each integral, but 0 is easier to evaluate, so let's split at 0. Kind of go back there. Then, okay, so if we're wondering if this original integral converges, if this area equals something and this area equals something, and then together they add up and equal something, then for this integral to converge, both of these have to converge. You can't have one converging and the other diverging and say the original converges. However many integrals you split this up into, they all have to converge for your original to converge. So just set up one of them and work with one for a minute, because if we work out this original for this first integral and it diverged, then the game's over. We don't need to know whether the second piece converges or diverges, because this one already diverges. It would force the original to diverge. All right, so n to 0, xe to the negative x dx, that's limit into infinity, xe to the negative x dx. If we use the u substitution down here on the left, we will end up with, let's see, n to 0, e to the u, negative 2 du, and the n and 0 are currently x bounds, not u bounds. So if we anti-differentiate, it would be negative a half e to our u value, and our u is negative x squared, and we're evaluating from n to 0. Now we're back in terms of x. Let's plug in a 0. Let's plug in an n. If we plug in 0, we get negative a half e to the 0 plus a half e to the negative n squared. And then take your limit. This first term, e to the 0 is 1, so that'll go to negative a half. This one, e to the negative n squared, that's the same as e over n squared. No, rather 1 over e to the n squared. And that denominator gets big, the numerator's fixed. That whole term goes to 0. So we're looking at negative a half. Times 1, e to the 0 is 1, so just negative a half. All right, so that first integral converged. So this area is negative a half. There's some symmetry going on here in our graphs, so this one is also going to converge to a half. They're going to add up to 0. So our original integral will converge to 0. If you set up the limit on the other piece, let's go into infinity, 0 to n x e to the negative x squared dx. Let's not skip a step. Let's use n to 0, e to the u over negative 2 du. We'd have plus a limit into infinity. And our antiderivative is the same as it was on the other side. And if we plug in, we have limit. You know what? On this last step, I'm looking at the other side. We did not need to. Oh, yeah, we did. Never mind. Okay, so we have limit into infinity, negative a half e to the 0 again, and negative 1 over 2 e to the n squared. This term again goes to 0. And oh, you know what? I evaluated in the wrong order. That's right. Okay. So this, let me erase those things. So negative 1 over 2e to the n squared plus 1/2 e to the 0. All right, this term goes to 0. The last term is going to be plus a half, plus 1/2. So if we bring those together, we have the 1/2 plus a negative half. Both of our integrals converged to a negative a half and a plus half. Together, they converge to 0. And the limit converges. So let's see, both limits exist. As such, our original limit we had before we split it into 2, or our original integral, rather, original integral converges to 0. All right, again, to just summarize that, we split our original integrand into our original integral into 2 integrals. Doesn't matter how we split them. If we split it 0, or if we split it 1 or 2 or 3 or negative 5, doesn't matter. Just splitting it 0 makes it easier to calculate. So we split the original into 2 integrals at an arbitrary value, and then both integrals must converge for the original to converge, and that happened. All right. Let's see, up next, we'll look at another improper integral or 2, and then we'll move into improper integrals where the integrand is unbounded. And the last thing, I guess, to take away from all of this is the picture does not tell the story. If we go back to the beginning, there's not a whole lot of difference between this region in pink. I mean, you have an infinite curve, and the area extends off to the right. Here, with 1 over x squared. So the last one was what? 1 over x to the half. Here it's 1 over x squared. Similar situation. You got an infinite curve. The area extends off to the right. I know it looks smaller, but the graphs are almost identical looking. And then even further down here, okay, this area, you have an infinite curve, infinite curve, and an area that looks like it extends off to the right here. Infinite curve, an area that extends to the right. Over here, infinite curves, areas that extend. But the picture didn't tell the story. In this case, the areas were finite, 1/2 and -1/2. In this case, the area was finite. You ended up with what, area being 1. In this case, it was 2/5√3. In that case, it was 1. In this case, infinite. It doesn't mean that there are more conversion cases. It's just that if you look at the picture, in all these pictures, it looks like the area is converging. Actually, in all these pictures, it looks like the area is getting bigger because it would just extend forever. But in some cases, it actually does get bigger, bigger, bigger. The area just keeps getting bigger and goes to infinity. In other cases, the area is finite. All right. That's it for now. Y'all take care. Have a good weekend and see you Monday.